So this panel have been very productive before even the panel discussion. Yeah, I'm good. Standing up, no problem. And they've actually produced some questions they'd like to discuss already. So we're going to show those on the slides behind. That means you can't actually see your own questions, but it should be okay. Maybe you can see them on the screen over there. I'll wait for them to come up. Okay. Do you have any specific place where you wanted to start with these questions? Can you see them from where you are? There's some on the screen. We can actually roll that screen across a little bit closer.
So, this is, let's start from the last question. It's something that Archie's-Man also introduced the first day. And it applies to gravitational wave data from LIGO Virgo, but also from Next Generation and also from LISA, including white dwarfs. So will we gain more information from single events like GW 190521 or from the population? So any feedback from the audience?
You need single events to make a population, right? So it depends on what you're after. If you're after a population, then you gain information about it from the population. While if you're looking for an exotic, a boson star, you are not going to discover a boson star, a whole bunch of boson stars at the same time. So you have to go after the single events as well. So it's very difficult to say what is more, what is better. This way. This is my opinion.
Some other comments from somewhere? Maybe one of the panel members want to address this. Abbas, did you want to say a few words?
I think I totally agree with that sentiment that we need the individual events as well as the population. But really the question is that at some point the population would start to saturate, right? So if we keep seeing 10 solar mass black holes merging with each other, would that really, and without any measurable, any other properties, and we consistently keep seeing that, then is it really contributing anymore or helping us constrain our formation models better? Or if, it really depends on what we are after, I guess.
But all your black holes will be different, I presume. They'll all have different spins, no?
Yeah, hopefully. If that's the case, then our population is perfect. Then we can look at the global properties from all those detections and compare that to what we get. But will that help us entangle is the question.
Well, I would say something maybe a bit provocative because we are tired. So I think that the single event drives the paradigm shift. Then the population can give us a way to quantify the uncertainties. I mean, there would have not been so much work on the upper mass gap and the pairing stability without the one event, 190521. There would have not been so much work on the counterparts, all the fantastic things that we learned today about the kilonova, the blue and the red, without 170817. And if we get a clear signature of eccentricity in LIGO and Virgo, this will also probably be a major revolution in the models. So this is against my current principle, ethic principle, but I realized that a single event can really be a paradigm shift. What about white dwarfs?
And so I think that in LISA we don't have, I mean, we can only think about a population because we will see all these binaries at the same time, right? And I don't think that even the brightest one is never going to be alone. They will come in few, maybe then more and more and more. And we have to study them as a population from both perspective data analysis, because each individual signal in the galaxy will affect all the other gravitational wave sources in the galaxy. For instance, when you think about this unresolved foreground that forms, right, that's additional noise for every other LISA source. But also as an astrophysical population, right, we will, if we see some overdensities of sources, we will maybe know that, you know, those can establish mass transfer and they're staying there for longer than we thought or something like that. So for sure, we will analyze individual sources to recover some specific masses and things. The brightest one will be the best. But like, I think that in LISA, we sort of constrained to think about the global picture.
Would a single event followed by a type 1a supernova be the holy grail or like the ultimate event?
Okay, I picked up the last question. Now I will either ask the public to choose one question, or otherwise I will ask Valeriya. So public, audience, colleagues, go now or never. Which question you want, or any other questions from me?
So while we're on that type 1a supernova, I'm going to go back to my question that I had, because you mentioned that we could have a type 1a supernova in our own galaxy and see it in gravitational waves and not electromagnetic radiation. And I was kind of surprised about that. Can you describe the kind of scenario where you'd expect not to see any electromagnetic radiation?
Yeah, so this is like, I mean, we don't see it because it is delayed so much that it's beyond 10 years of the extended LISA mission. And that happens in these classical scenarios where from the 80s, now where you have two white dwarfs that with the total mass of Chandrasekhar or more, that really come together by gravitational wave radiation. And so you have sort of the same situation as LIGO sources, that they merge together. And hydro simulations predict that there may be some delay, although those delays are not constrained, like there are options up to thousands of years. Now, in that case, yeah, but I have nothing to do with that.
So that's the resulting emission you're talking about.
Yes.
But we'd actually, I would assume we'd see the two of
It's
them
because,
like spiral towards each other.
Like it needs to simmer for a long time and then it detonates after years or thousands of years, and then you have type 1a. So you merge, you simmer, and then you detonate. Yeah.
Wow. Okay. Didn't know this. Thank you. I've learned something. So whilst we're still on the binaries, the white dwarf binaries, I'll choose now. So what can we still do to identify the whole population of galactic white dwarf binaries? Because I think with the electromagnetic radiation, we could probably identify a large number. Do you have any ideas about what we should be doing to try and find those before LISA's launched, so you know where those binaries are and have some information about their parameters?
Yeah, so although we will never be complete as with LISA, but we can like use, for instance, Gaia to search for the candidates, to have as homogeneous on the sky sample as possible. And what I really like of Gaia, that we can look, yes, at short orbital periods, but we can also use astrometry or, astrometric motion to look at different regimes. And though, like, even that they are will never merge, right? They will help us to constrain those that merge. So I think it's really important for my community to look not only in the short orbital periods, but across different periods. And then in those regimes, we would be able to constrain different mechanisms that govern the shape of the population, and then that help us ultimately to come to short periods as well. So I think that Gaia would be important in finding candidates, but we also need spectroscopic surveys to follow up all of them. And white dwarfs are very faint, so they need long exposure or a high cadence timing if we want to look for eclipsing or photometric variability.
So essentially Gaia, and we still need to exploit a lot more of their data then in that case. So you're saying a lot more needs to be done still.
Yeah, and for instance, ZTF is one of the ones that discovering a lot of these binaries, and simply because they're staring at the galactic plane, they can afford that. And just by staying there and looking for long enough, you will definitely find those, more of those binaries.
So Rubin as well, then in that case, will be an excellent facility for doing that sort of thing. I mean, obviously, it's not got the same astrometric precision as Gaia, but.
Yeah, the only thing that like the cadence of Rubin is maybe not as optimal because so in the LISA regime, we are really, right, we're talking about periods of less than an hour and eclipses of photometric variability of minutes. No? So it really needs high cadence observation. So maybe again, like similar to Gaia, we can figure out the candidates and then have the high cadence or spectroscopy to follow up.
Thank you. So some other question you want to choose, or otherwise Michela chooses, or tell someone else to choose?
Could go towards the open questions. Those are always fun to discuss. So, maybe the first one with, regarding the study of the progenitors, like in terms of, maybe we can phrase it in a different way. Like we do a lot of modeling. What do you think our models totally get wrong, or something which we are so uncertain about that which can really affect the final results? So from evolving progenitors to the final compact object binaries that we produce.
Sorry, let me rephrase. You mean, can we already reject some of the model? Is that the question?
With regards to the physics that we have, which one, what needs to be
Is this sort of thing addressed on the next slide? Because there were some things about spins and various things.
There's stuff on the next slide as well to just guide the discussion in case.
Like this?
So, yeah. The first one is about the disentanglement there, but the second one here, like the winds and remnant masses, natal kicks, some of these things we already mentioned in our talks, but is there something which we are really uncertain about, which can really affect the final results strongly?
I will be short for double white dwarfs is the common envelope, right? Because to form this very short binaries, you really need like efficient shrinkage of the binary, and that's the measure uncertainty. So we have a code comparison project going on where we will try to pin down the astro uncertainties into the LISA forecasts of the foreground and resolve sources, but yeah, the common envelope is the assumption that basically introduces the larger uncertainty. So if we can figure out that, it would help a lot.
I could either keep talking, or is there any comment or questions from the audience? Going once, going twice. Okay, then I will follow up on the comment by Valeriya. Yeah, it's nice to see that the common envelope is a good culprit also for the higher mass regime. And remarkably, in the higher mass regime, it may be the culprit for the opposite reason. So for binary black holes and black hole star system, things would be much better without common envelope. So this is interesting because for binary white dwarfs and binary neutron stars, in order to match the data that we have already now, you need the common envelope and need to this common envelope to be efficient in shrink the orbit of the system. For the progenitors of binary black holes, you'd rather get rid of common envelope or make it much less efficient shrinking the binary. So this is something that the data are telling us in the last few years, and that may drive really some important change in the field. Then I can go more into technical details, but I'm not sure.
Yeah, how do the black holes come together in that case? How do the black holes come together in that case?
A stable mass transfer alone.
Okay.
So I mean, just for people interested in Gaia, we have 3 Gaia black holes at the moment. Good ones, which means binary system where there is one black hole, stellar-sized black hole, with a stellar companion, and the stellar companion is nearly solar mass star in all the 3 cases. And they are called dormant black holes because there is no detectable X-rays. Of course, these will not become sources of gravitational waves, but for 2 out of 3 of them, the orbital period that we observe is too large to be consistent with the description of common envelope, and too short to be consistent with non-interacting binaries. So, and the same things, in the end, the same hint is something that we get from the excess of the merge rate of binary black hole. So maybe for the progenitors of binary black holes, something is going on that does not make common envelope as efficient as it is for low mass stars.
Not at all. Thank you. So I'm not an expert, not at all. So don't kick my ass if I'm saying something bullshit. But so so my question is regarding the spin of black holes. So from the data we have from LVK, it seems that black holes have a low spin, right? But is this a bias introduced for from the modeling of the waveforms, or for the evolution in the binary, or we can assume that it's not a bias and almost every black hole, also the isolated ones, have low spin?
Let me start, and if there are some LIGO Virgo people who also want to add something, please just chime in. So let me say, I would say there is no bias, although if you look at the uncertainties about the measurement of the spin from gravitational waves are pretty large, which is one of the reasons why I'm looking forward to the next generation, to the Einstein telescope. At the population level, however, we can say that there is a preference for non-maximally spinning black holes, although not vanishingly small spin, at least not for the entire population. And I think this is very important to keep in mind, especially in comparison with what we observe from the low mass and high mass X-ray binaries, especially the high mass X-ray binaries, even if there are only 3 of them in the end or so, that seem to have more like maximally spinning black holes. But from that point of view, it depends on the biases of the electromagnetic observations. And I don't know if there is someone here who wants to comment about the biases of the electromagnetic observations of spins. I would also mention another thing. Well, let me mention two, and then Abbas, if you want to add something or someone else. One is that it would not be a shock for the models if most black holes are low spinning, because this would be consistent with other observations that come from astroseismology about the way stars transport angular momentum. So it wouldn't be shocking, although it is interesting. And the second consideration I want to make is about the few systems that seems to have support for spins. For instance, again, 190521 has mild support for spins, possibly large spin in the orbital plane, which I think make it particularly interesting. I have one set of models that I have not shown because they are dynamical models where there is quite a one of the few straightforward prediction, not just by me, but in general, that if there is a significant contribution from the hierarchical mergers in the population, so from mergers of smaller black holes to bigger black holes, then we should see a signature in the spin distribution of LIGO and Virgo at around 0.7, speaking of the dimensional spin. And this will appear at some point. It should appear, otherwise the GR is wrong. When we'll set the percentage of hierarchical mergers that we observe.
I agree with this, that when two black holes merge at the hierarchical merger scenario, you should end up with a higher spin. So when that black hole merges again, then there should be some signature there. I think there's one event which has chi effective close to 0.7, if I'm correct. But uncertainty is huge on that, yeah. But that would be definitely interesting.
Thank you. Hello. Yeah, I just wanted to comment from a data analysis point of view. The measurement of the spin is mostly influenced by the priors now, and what is commonly interpreted as the black holes we observe have zero spin is the fact that we assume a prior that is uniform in the sphere for the spins, for the three-dimensional spin of each black hole, which manifests itself as a pointy priors at zero for a single component. So yeah, what Michela was saying is correct. Like it's not a problem of bias, but it's a problem of the amount of information that we're able to extract now, which is very limited.
So is there something else on that list that could be strongly improved to improve our models so that we understand a little bit better what's going on?
From the observational side, what we really need to help better constrain our prescription. So these Gaia black hole detections are really useful because they're already indicating, and I think we should be more holistic in our comparisons from our models, whether we can nail down well-observed systems within galaxies and whether both our dynamical and population synthesis codes are able to reproduce really all the binaries we see across different mass ranges with different compact objects. So I think in that sense, the Gaia black hole detections are quite important. And I think there are a few also Gaia neutron stars detected. Are they challenging any ideas about common envelopes or other processes?
They are just candidate because they have too low mass. So I'm looking forward to the DR4 and also additional follow-up to confirm whether these Gaia neutron star candidates are really there or not.
Now I was just going to talk about black hole 3 actually. Black hole 3 from Gaia, because it's got a high mass, much higher mass than any of the other black holes that we know in our own galaxy. Do you think that there must be many more of these black holes, so massive black holes in our own galaxy, given the kinds of masses we've been observing from the gravitational wave events?
So it could be many more, but it's definitely indicative of low metallicity formation for this, because there's also a nice association of Gaia black hole 3 with a disrupted star cluster, and the stream of this disrupted star cluster, which was probably an accreted star cluster during a merger of a dwarf galaxy with the Milky Way. And in those low metallicity environments, perhaps it's possible to form such black holes, but really future data releases will point out if more of these black holes are out there. And yeah, they can be quite interesting from the point of view of knowing also the formation history of the galaxy itself. This is also an interesting detection at 30 solar masses, but I think there are also some high mass X-ray binaries like SIG-X1, where the metallicity is higher, but the new black hole masses are of the order 20 solar masses. So if those are consistent, yeah, it would be interesting to nail down the evolution of those sort of binaries as well.
Or maybe it may be more interesting the other way around. So we expect, roughly speaking, about 100 Gaia black holes from the R4, which will come in 1 year and something from now. And the Gaia black holes tell us the metallicity, because you can constrain the metallicity of the comparison. This does not come from LIGO and Virgo. So I'm wondering, what if we find another black hole as massive as Gaia black hole 3, but with high metallicity? That would be a stretch to the model. If we just keep finding Gaia black hole 3 like things with low metallicity, that wouldn't be a surprise. If we don't find anything, that wouldn't be a surprise either, because we don't have that many very metal poor stars in the Milky Way.
Yeah, so you're basing that on the companion star, but I mean, what if there's been several dynamical processes that have formed that binary? You might not be able to trace it back to the original companion.
Oh, this is maybe something missing also in the discussion to do your question for the dynamical formation of binary white dwarfs. Dynamics has a strong preference for high mass systems because they have more binding energy, so they are more energetically stable. It means if dynamics is effective, you tend to suppress binary system with a massive companion and a low mass object. You tend to, you have more likely systems composed of two massive stars. So this is an argument, although with some caveats.
Okay. From behind.
Thank you. For these GW events with EM signal from the same source, are there some information from EM signal can be useful for the parameter estimation of GW, or what are they?
You mean electromagnetic counterparts during the merger, or other electromagnetic observations not immediately related to the...
I mean, both of them.
Okay, oh, that's broad. Let me start from the electromagnetic counterpart. Maybe I will let Abbas just comment on the AGN disk scenario, which is the only one, or the most likely one, where you expect also an electromagnetic counterpart for the binary black holes. And then all the information that we can get from the electromagnetic counterpart of a binary neutron star or black hole neutron star is, of course, relevant. But recently in our group, we moved also toward the additional electromagnetic observations that are complementary and that can give us insight. For instance, the rate of a peri-instability supernovae that can help constraining the rate of black holes connected with the mass gap or above. And peri-instability supernovae are very bright, so they are something that you can observe pretty easily, and actually you see 1 plus or minus 0, plus or minus 1. Or the evolution of Wolf-Rayet stars, which are very likely black hole progenitors, and there are some Wolf-Rayet stars in the local universe that have issues, like the low metallicity the Wolf-Rayet stars in the Small Magellanic Cloud, which is a low metallicity environment. So there are many. This is just to say, to wrap up, that there are many electromagnetic observations not related with gravitational waves directly that provide key information and we should use in the right way in the models, in a holistic way and in the right way in the model.
Similarly, also for the dynamical environments, we know some young massive clusters where if you have black holes in them, then they can be in binaries with massive stars, and then you could get these ULXs in these young massive clusters or some other X-ray binaries. So those can also be strong constraints on making these sort of predictions. Then also another important thing is that if black holes are growing in clusters by colliding or merging with stars, what kind of, a lot of people have looked into those sort of microtidal disruption events and then figure out what could be their rates as well from dense environments. And then if we observe them with future transient sky surveys, that could then help also also try to constrain how accurate our models for those dense environments and collisions are. With regard to the AGN scenario, this is also something interesting, which we didn't talk about much, but in the disks of, in the gaseous disks around supermassive black holes, you can get these migration traps where you can have stellar mass black holes come in and be trapped in certain orbits and other compact objects as well. And they can grow in there and they can also interact with each other. And if you can merge a binary black hole inside there, then you can have some flares in the AGN disk, which could potentially be observed, and that would be strong counterpart. There was one very weak claim of, I think, GW 190521 claim being associated with such a flare in an AGN disk. But maybe in the future we can have better localization or something which can be really indicative that this is coming from an AGN disk, or maybe some signs of eccentricity in a merger along with some electromagnetic counterpart. Yeah.
So we've got time for one last question, something pressing. Okay, cool, I get to ask it. So earlier on you were talking about the black holes that we finally found in the globular clusters, and there's a number of them been found. Through mass segregation, you might think that they would sink towards the center of the cluster, but the majority of them have actually been found sort of, I mean, there are somewhere towards the center and in the half mass radius, for instance, but they're not right in the center. Is this indicative of maybe some dynamical processes that are going on?
Yeah, that's absolutely possible. These binaries, they could have been heated from the center. They could have been closer to the center, but then interactions within them could have then some recoil, which parks them towards the half mass radius. That's a possibility. But yeah, it depends on the whole overall cluster evolution as well. How many single black holes are also in there? How many binary black holes could also be in there, which could be heating, providing, which could be responsible for parking these binaries outside. But yeah, most of them are still within the core of these clusters, so that's expected.
Yeah, and there is the new candidate in Omega Centauri for an intermediate mass black hole from the proper motions. Well, it's the first time that something else compared to Sagittarius A star gets constrained to some extent by looking at the proper motion. So, and there are hopes to get constraints also from the acceleration. So I think that's a fantastic news.
Just add to that, I think that is our best candidate for an IMVH in the very recent times in a globular cluster. And most likely Omega Cen itself has a very interesting history, that it's most likely the nucleus of a strip dwarf galaxy which merged with the Milky Way. So it's really, if these observations constrain the mass, which put it at a minimum mass for 7,000 solar masses, this is really something which has been eluding us for a really long time. So
I'm not sure which paper you're referring to. I mean, there's been these kinds of proposals that are these.
So this is from last year. This is Heberle and collaborators. It's a Nature paper which looked at over 25 years of HST astrometry in the center of Omega Cen, and they find 4 or 5 stars very much in the center, which have 7. But I think 4 are really in the center. There are a few further out, which have velocities which are higher than the escape velocity of Omega Cen. And they can be explained by being bound to an intermediate mass black hole. So,
because there's been a lot of searches done in different ways,
different
in different wavelengths, looking for.
Yeah, it's different from what has been done before, and is at the moment possible only for Omega Centauri, because there are these 25 years of data of HST that were reanalyzed together. And it is only possible for Omega Centauri for a blend of being sufficiently nearby, a common target of HST, like everyone wanted to look at Omega Centauri, so there are all of these data, and not being too crowded in